Good afternoon, everyone. Hello?
Hey.
Okay. Oh, it works. Okay, good afternoon, everyone. Welcome to this session where we have three wonderful papers. My name is Ana Lucia Vorbănescu. I work at the University of Twente in the Netherlands, borderline Germany. And we have three exciting talks today. So we're going to start with Santosh Pandey. He is a researcher at the PhD student at the Stevens Institute of Technology. His research focuses on high-performance computing, graph processing, and machine learning. And we're going to see at least 2 out of the 3 in this talk, entitled Scalable Deep Learning-Based Microarchitecture Simulation on GPUs. The floor is yours.
Thank you for the introduction. Hi, everyone. Good afternoon. I'm Santosh Pandey from Stevens Institute of Technology, and today I'm presenting our work, Scalable Deep Learning-Based Microarchitecture Simulation on GPUs. And I promise all of you that this is going to be an interesting talk. So let's start. So for my talk, I'll be starting with background on the importance of microarchitecture simulation, how traditional and ML-based microarchitecture simulation work, how state-of-the-art ML-based simulator SimNet works in detail, and then challenges and optimizations with SimNet, and then I'll conclude my talk with experimental setup and results. So let's start with background on microarchitecture simulation. So microarchitecture simulations are tools which are used to evaluate the performance of any given microarchitecture configuration. And we can find their application in hardware design space exploration. For example, we need to come up with a microarchitecture design which can meet a certain performance goals. So for that, we have 2 parameters, for example, cache and branch predictor. And each parameters have a huge design space. For example, here, cache has size and replacement policy. So based on these parameters, we come up with a microarchitecture configuration. And our goal would be to evaluate this microarchitecture configuration with various benchmarks. So for this evaluation, we can use popular benchmarks, Spec CPU 2017, and it has various programs. Here I have 538 and 619. So this benchmark represent image manipulation application and fluid dynamics application. And the main goal over here is to simulate this microarchitecture to get the performance. And simulation is a software model of this microarchitecture, and we use this software model to evaluate the performance. So for evaluation, we can use performance metrics like CPI, cycles per instruction. After we have CPIs for these benchmarks, we can use them as feedback to update our microarchitecture design to meet our performance goal. And with this, microarchitecture simulators are important tool which can help us evaluate a design without doing any fabrication. So let's see in detail how traditional microarchitecture simulators work. So Gem5 is one of the popular microarchitecture simulator, and it implements a software model which you have to develop yourself in Gem5 for the microarchitecture configuration that you want to simulate. And for simulation, we can take an example of 619 benchmark, which is compiled, and then we can get instruction. Here I have 3 instructions. And our goal is to predict the latency of all these 3 instructions. So this simulator performs cycle-accurate modeling, which models each and every component of the hardware, including 5-stage pipeline and all other steps of hardware. And with this kind of detailed simulation, we can find any data dependency between instructions. For example, here, the sub instruction and LW load instruction have dependency of EDX, as they are both trying to access the register EDX. So with this kind of modeling, detailed modeling, we can get accurate behavior of the hardware. So that's the main advantage of traditional simulation. So these traditional simulations are detailed and accurate, but they are very slow. And if you want to simulate real work benchmarks, it may take weeks or months to simulate all the benchmarks to get their performance. And the main problem with these simulators are that they are highly irregular and they are difficult to parallelize. So we cannot leverage modern accelerators like GPUs and TPUs to accelerate this kind of simulation workflow. Now let's move on to ML-based microarchitecture simulation. So for ML-based microarchitecture simulation, we replace the highly irregular software model with a trained machine learning model. And instead of doing cycle accurate prediction, what we do is we perform instruction-wise prediction. So we can sequentially go through all of these instructions and do single shot prediction. So the main advantage of, the choice of the model for this kind of machine learning simulation could be convolution neural networks, sequential models like LSTMs, or we can also use attention-based models. And these kind of models are highly regular, and they are also parallelizable. And we can leverage modern accelerators like GPUs and TPUs to further accelerate their performance. And that's the reason why we want to do machine learning-based simulation. Now let's move into details on how a state-of-the-art ML-based simulator works with SimNet. So we have the same program that we need to simulate. And for the program, we need to generate the input features for those instructions to perform machine learning-based simulation. So for that, we use functional simulation with cache and branch prediction. And with that, we generate numerically represented execution trace. And this kind of trace have two categories of features. So first one are static features, which represent the static property of the instruction, like the operation type, the registers that the instruction is using. And the other category is dynamic features, which try to represent the dependency between the instruction and the hardware behavior. So some examples are if multiple instructions are trying to same address or not, what's the state of branch prediction. And we combine these two features to get a 50-dimensional representation of each instruction. So after we have this input feature, we can start simulation. So let's see how the simulation workflow goes with first instruction load word. So for this kind of prediction, we first copy the data, first instruction to instruction queue. And this instruction queue tracks all the active instruction, because active instructions can have data dependency, and with this queue we can get all the required input of all instruction that can impact the performance of that instruction. And the data is then moved to input, or we construct the input from all the active instruction in the instruction queue. And as we only have one instruction for first instruction, we include paddings over there. So the reason we include paddings is that machine learning models require fixed size input. And for that, we include this padding. Now that we have the input required for inference, we move this data to GPU first to perform inference in GPUs. So before we could perform inference on this data, the data is again transposed. So we do this transpose so that we could align all the features of instruction for machine learning model. And with the input ready, now we can perform the actual inference. And here I have an example of 5-layer CNN model used by SimNet. And in this 5-layer model, the first 3 layers are 1D convolution, which is followed by 2 fully connected networks. And more details on how we can train these kind of models and what are other choices of model, we can look into the SimNet paper. Now, the way this convolution works is it slides over the input channels, and then it gives the prediction. And the prediction of the output of first layer is then transmitted to the rest of the layer so that we could get the final output. And now let's move on to how second instruction is predicted. So we have the same workflow. The instruction is first copied to instruction queue. And as you may notice here, the earlier instruction is still in the instruction queue because that has not finished its execution, and it can impact the performance of the add instruction. And based on that, we move both copy both instructions to construct the input. And here, the first instruction is current instruction, for which we need to perform the prediction. And the second instruction here is the active instruction, which we also term as context instruction. And then the data is similarly copied to GPU, and then it is transposed, and then we can perform the final prediction. So this is an overall workflow of SIMNet. Now let's move on to challenges of this workflow. So there are two challenges associated with this current workflow. The first one is 4 redundant data copies. So while preparing the input for inference, we have to do data copy 4 times. And the second one is inaccurate parallel simulation. Now let's move on with challenge 1, which is 4 redundant data copies. So first of all, the instructions, all these instructions are functionally simulated to get the execution trace, and they are placed in disks. So the first copy is when we copy the instruction from disks to instruction queue in CPU. And then we need to copy that instruction again to prepare the input. And we add paddings, and then it is copied to GPU, which is third copy. And again, we need to perform a transpose, which also incurs a new data copy, which is fourth copy. And so before we do prediction, we have to copy the same instruction over 3 devices 4 times. So that's very inefficient. Now let's move on to our optimizations. So our first optimization is GPU-based input construction. So previously, we placed the instruction queue in CPU to prepare the input in CPU, but we can just move that instruction queue into GPU so that we could directly construct input in GPUs, and we can reduce 1 data copy. So 4 data copies are reduced to 3 data copies. Our second optimization is sliding window-based instruction queue. So this sliding window instruction queue replaces the earlier instruction queue, because for earlier instruction, we cannot use instruction queue as input itself, because the input requires different orders, and then it also need to include padding, which cannot be done in earlier design. So let's see how sliding window-based instruction queue deals with that. So first of all, we perform reverse batch copy. So multiple instruction can be copied to the instruction queue at the same time in reverse order, and that also amortizes the data copy cost. And one more thing is that we can also overlap this data copy with further simulation steps. And after the data are copied, we introduce some paddings, and the key point over here is how we define input for each instruction. So for the first instruction, we have this red window which points towards the first input, and this red window is implemented with certain pointers to point to the start and end of the input. And the interesting thing over here is when we need the input for next add instruction, instead of copying the data again, what we do is slide this window. And by sliding this window, it means that we are adding some offset to the pointer. And with just that, we can get the input for next instruction. And with this, we reduce 3 data copies to just 1. Now let's see how we can remove the last data copy with transpose. So for third problem, which is related with transpose of instruction, we transpose this input so that the features of each instruction are aligned for convolution. For example, here I have 3x2 convolution channel going over the input. And the first thing that we can do is, instead of transposing the input itself, we can transpose the convolution channel itself, which is a one-time cost. And with that, we can just slide that convolution over the input, and that avoids doing any transpose for the input. And our next optimization is unwanted computations over padding. So as you can see over here, in the input from 3 instructions, we only have 1 instruction, and 2 of those fields are paddings. And when we do convolution over those paddings, it is unwanted convolution. So we will also like to avoid those kind of unwanted computations. And for that, what we do is dynamically adjust the convolution width based on the number of instructions present in the input. So for example, here we have only one instruction as input for the first instruction. So we can reduce the convolution channel from 2 by 3 to just 2 by 1. And with that, we can also avoid computations over paddings. So, and for supporting both of these optimizations, we develop a custom convolution kernels. So that's how we can reduce 4 data copies to just one or non-amortized copy. Now let's move on to second challenge. So the second challenge is inaccurate parallel simulation. So I have here 6 instructions as an example, and the nature of simulation is sequential due to the data dependency among the instruction. And this kind of simulation is very slow. And the next method is parallel simulation, which is also adopted by SimNet. And for this parallel simulation, what we do is partition the whole instruction into multiple partitions. So for here, we have partitioned these 6 instructions into 3 instructions, each of 2 partitions. And then for each of these partitions, we can do parallel simulation. So it is definitely faster, right? We can have many processors, many partitions, and we can simulate them in parallel. But the main drawback over here is that with this kind of partition, there is loss dependency between the instruction because simulation is sequential in nature. And for example, here, the JLE instruction of partition 1 can be dependent on 2 earlier instructions, add and sub from partition 0. So this kind of partition results in inaccurate prediction. And the earlier instruction has more chances of getting higher error because that's the point from where we break the dependency. Now let's move on to some empirical evaluation. So for 17 spec benchmarks, we tried to do parallel simulation. We're starting with 32K partitions to 128K partitions and compare the simulation error with sequential simulation. So for 32K partitions, the average error is around 8%. And when we increase the number of partitions to 128K partitions, the error grows significantly. And so with more partitions, we can get more parallelism, but we also introduce more error for simulation. And hence, this kind of simulation is also inaccurate. Now, let's see how we can correct this kind of simulation error. So the main challenge for correcting this simulation error is how we can acquire the missing context for partition 1 so that we can reintroduce the dependent instruction. So for that, our first solution is to perform warm-up. So for warm-up, what we do is we simulate an instructions from earlier partitions. So for partition 1 here, we simulate 2 instructions, add and sub from partition 0. And then we can do the simulation. So warm-up is quite effective, but it fails to fully recover the correct context because the main challenge for warm-up is how can we determine the correct value of n. If we have less number of n, then we may not acquire all the context. But if we have very huge value of n, then we are doing redundant simulation and our simulation cost also increases. So to tackle that problem, we have next solution, which is to do post-error correction. So here what we do is earlier partition corrects first few instructions of next partition. So for here, after partition 0 and partition 1 finish their simulation, we use partition 0 to correct first few instructions of partition 1. So here, partition 0 corrects JLE and sub-instruction prediction for partition 1. And we perform this kind of correction till the number of context instruction for both partitions is same. For more details on how we figure out number of contexts and how we compare them, you can look into more details in our paper. So with that, let's move on to experimental setup and results. Starting with experimental setup, So for our experiment, we use DZX 800 server, which has 800 GPUs, and we use this server for single GPU performance and then performing state-of-the-art evaluation. And for our scalability test of our simulator, we use Summit supercomputer, which has V100 GPUs. And for our evaluation, we use the default O3 CPU from Gem5. And for all the simulation error, we compare our simulation error with Gem5. Now let's start with the results with challenge 1, like how we can remove the redundant data copies. So for that, we actually have 5 optimizations, of which 3 of them GPU-based input construction, sliding window-based instruction queue, and custom convolution layer are discussed. And 2 more optimizations, optimized inference and pipeline simulation is described in the paper. So with our optimization, without any optimization, the base performance is 0.14 million instructions per second. And with our optimization, the simulation throughput increases, and with pipeline simulation altogether, we achieve 3.024 million instructions per second. And this is 21.5 times speed up over the baseline. And our next challenge is to get accurate parallel simulation. And for that, we compare the simulation error for 17 benchmarks without any optimizations and with optimizations. So the baseline error is around 17% on average. And when we introduce warm-up, the simulation error reduces to around 6% on average. And with introduction of correction, the simulation error further decreases to 2.3% on average. So this is significant reduction in simulation error while achieving higher parallelism with more partitions. Now let's move on to comparison with state-of-the-art. So for state-of-the-art comparison, we compare our work with Gem5 itself, sequential version of SimNet, JetSim, which is one of the parallel simulator, and we compare our work with single GPU and 282 GPUs. So for Gem5, the throughput is 0.2 million instructions per second, and for sequential SimNet, it's much lower, 0.005 million instructions per second. And for JetSim, it is around 16 million instructions per second. So JetSim is one of the parallel simulator, but its parallelism is limited to number of cores, and we cannot scale this simulator further. And for our single GPU version, as we discussed earlier, the throughput is 3 million instructions per second. Now, for our 282 GPUs version, the throughput is 553 million instructions per second. And that is more than 2,796 times speed up compared with Gem5 simulation. And it also accounts 3 order of magnitude speed up while achieving similar accuracy as Gem5. And now comparing the scalability with increasing number of GPUs, our speed up is also almost linear. And comparing the throughput for same number of GPUs but larger number of instructions, if we have more instructions to simulate, we can get more throughput as the parallelism is higher and the overhead of doing error correction is also negligible. And more details on use cases and simulating different hardware configurations can also be found in our paper. And in conclusion, we achieved more than 3 order of magnitude speed up over cycle accurate simulator Gem5. And we propose optimizations for parallel, accurate, and efficient machine learning based simulation. And the optimizations that we discuss here are also applicable to other ML-based simulators or ML-based instruction predictors like iThemal. And you can find our source code in the GitHub link below. And I would like to acknowledge Brookhaven National Lab for their support. And if you have any questions, you can also contact me, and my email address is over here. Thank you so much for listening. Any questions?
Thank you very much. Questions we have already in the back, so can you take the mic?
Hi, thanks for the presentation. What's the size of the CNN and how does it scale with the complexity of the microarchitecture, for example?
That's a good question. So right now, the model that we use for our evaluation is just 5-layer CNNs. And for, I think for first, second, third layer, we have around like 2,048 number of parameters for all of those. And for convolution channels, I think we have 128 for first layer and then 256 convolution channel for other layers. And for the second part of the question, for different microarchitectures, we have not evaluated that yet, but think the similar kind of model should be able to get same accuracy. Obviously, you can have larger model to get more accuracy, but for different configurations, the model design could be similar.
All right, and a short follow-up. Have you considered other types of accelerators for this relatively small neural network, like FPGAs?
No, we have not done that. We have just experimented with GPUs only.
All right, thanks.
Hi, really nice talk. I just want to know how many features did you consider for your, to extract, to perform the model prediction? How many features, like static, dynamic, how many features?
Yeah, so for our model, let me go to the slide. Yeah, so we have altogether 50 features, and for static features, we have 27 of those, and for dynamic features, we have 23 number of features.
So you also said that the overhead is negligible, right? So you need to extract the features at runtime, right?
So the overhead,
how did you do that?
The overhead that I discussed earlier is for error correction techniques, not for gathering these features.
You didn't evaluate like the overhead of gathering the features, right?
Oh yeah, so in current evaluation, we have not included the overhead of gathering all these features, but even while considering all this overhead of feature extraction and then training the model, if we have like billions of instructions to simulate, the overhead would be negligible. And in simulation, in real world, we have to like, each benchmarks can have billions of instruction, and we have to evaluate multiple benchmarks. So the overhead would be negligible.
Thanks.
Time for one more question, so we'll take the one in the back.
Hi, I'm Matt Sinclair, University of Wisconsin. Thanks so much for the really interesting talk, Santosh. So I guess my question is it really, kind of following up on the first question, there's been work on running Gem 5 on FPGAs before, like RAMP and Mohammed Alian's work at the University of Kansas that's kind of concurrent to yours. Wouldn't that be a fair comparison to SimNet in terms of like how much better you're getting? And I guess just if I can ask a related question while I'm at it, Gem 5's O3 CPU model is not the most accurate model in the world. So if you're getting similar accuracy to that, is that kind of concerning because you're not really close to the real hardware then, if it's not close to the real hardware?
Yeah, that's a great question. So I'll start with your second question. So the evaluation of this model are actually done in SimNet, and for that we also compare the accuracy of that with A64 processor, and that's I think that's hardware verified, and even for that configuration we can achieve similar accuracy. And for your first question, we have not evaluated Gem 5 with FPGAs, but I think even I have not gone through that paper, but I think even if we try to use FPGA for like Gem5 simulation, the parallelism could be somehow limited. But with ML-based simulation and doing this parallel partition, we can have like a large number of, a huge degree of parallelism compared with that.
Okay, let's thank the speaker one more time.
Thank you.